Okay, so this lesson is on 21.2, concentration and solubility. So the main idea is we're going to be talking about what it means for a solution to be concentrated, and then we want to be talking about the solubility and what that means for a substance as it dissolves. So the essential questions we want to be able to answer, we want to be able to answer we want to be able to represent concentrations in different ways. We want to understand what solubility is. We want to know the differences between saturated, unsaturated, and supersaturated solutions. And then we also want to be able to describe how pressure and temperature affect the solubility of gases. Some new terms for us: concentration, solubility, saturated solution, unsaturated solution, as well as supersaturated solution. So first off, when dealing with the term concentration, we are talking about how much solute we have in solution. So remember, a solution has two components. There's the solute, which is what's being dissolved, and then there's the solvent, which is what's doing the dissolving. Officially speaking, we would say that the solvent is whatever's present in the greater amount, and the solute is whatever's present in the lesser amount. So solvent is always greater than the solute. However, there are some circumstances where that can kind of get confusing, especially when we're talking about solutions where we're not necessarily doing your stereotypical dissolving a solid in a liquid. Okay, and so here I have three images where I have the solute particles represented with red and the solvent particles represented with blue or turquoise. Yesterday we learned precisely how a solvent will surround and solvate the solute particles, whether they're ionic or covalent, and kind of pull them apart. And so we're moving on from that. So if I look at the image on the left here, I would say that solution is not very high concentration, whereas the solution on the right is going to be considerably higher in concentration than the one on the right. So when I describe the concentration, I'm really providing a description of how much solute is dissolved in the solution. If there's not a lot, then the concentration is low. If there is a lot, then the concentration is high, and then anywhere in between. And so we could represent concentration in different ways. Some common concentration measurements are percent by mass, where we're taking the mass of the solute that's dissolved divided by the mass of the entire solution. We could also do that with volume, so the volume of solute divided by the volume of solution. So percent by mass, we often, things that you'll find in the pharmacy department of like Walmart, like creams that have special drugs in them, like let's say an anti-itch cream, it might have an active ingredient. Well, it's going to say on the side what that active ingredient is, and it's going to list its percent by mass. And so that's where you kind of see that one. For percent by volume, whenever you buy some type of chemical at the store, like Home Depot or Lowe's, it will often list the percent by volume of that chemical. If you ever in the future go into the store and buy alcohol, alcohol is listed as a percent by volume. So if something is 40% alcohol, that means that there's 40 milliliters of ethanol per the entire volume of the solution. So percent by mass, percent by volume, those show up a lot when you go to the store and things like that. But when studying chemistry and using any concentration, when you're talking about in terms of science, we will more often use the concentrations of molarity. I guess I should just say we'll use the concentration of molarity. Molality and mole fraction also exist, but they don't show up near as much as molarity does. And so molarity is what our worksheet will be on later. It's going to be the moles of the solute divided by the liters of the solution. Notice that the three that we're most familiar with, so percent by mass, percent by volume, and molarity, they all have solution in the denominator, not solvent. Okay, so it's the mass of the solute, the volume of the solute, or the moles of the solute divided by the mass of the solution, the volume of the solution, or the liters of the entire solution. So, for example, if I was dealing with the percent by volume of a juice in the juice section, if it said that it was 10% juice, then what that means is that there's 10 milliliters of juice, and then for every 100 milliliters of the entire solution, so 10 milliliters of juice plus 90 milliliters of water, it would be the entire solution. And then if I want to know the percentage of the juice, it'd be 10 milliliters of juice divided by that entire volume of the solution. And then we can compare the solubilities of substances as well. And so some substances dissolve in other substances, or they're soluble in other substances quite readily. For most solutions that we're going to be talking about in chemistry, we're talking about how it dissolves in water. But we could have a whole myriad of different types of solutions. For example, I could have a solution where one metal is dissolved in another metal. We call that an alloy. The air that we breathe is a solution. It's mostly nitrogen, so one could say that there's a certain amount of oxygen dissolved or in solution with the nitrogen. Okay, and so solutions are always something where they're uniform mixtures that are homogeneous, and there's always going to be something that's present in a smaller amount, something that's present in a greater amount. The smaller amount is the solute, the greater amount is the solvent. And so when we're talking about making solutions, some things do or don't dissolve in the solvent. So if I have, for instance, if I were to take a spoonful of sugar and dump it in water, we would expect that to dissolve. But if I took a spoonful of sand and I dumped that in water, I would not expect that to dissolve. So we could say that sugar is soluble and sand is not soluble. Okay, but solubility is a little bit more than just the black-white, does it dissolve or doesn't it dissolve. Solubility is a spectrum. So depending on the type of substance that we could have more or less dissolve. Okay, and so we define solubility based on how many grams of the solute will dissolve in 100 grams of water. So if I take 100 grams of water and I can dissolve 20 grams of whatever I'm talking about, then I would say that the solubility of that substance is 20 grams per 100 grams of water. Okay, so depending on the identity of the substance, the solubility will vary. So here is a table of some common substances. We have solids at the top of the table and gases at the bottom of the table. And so our main example for salt, sodium chloride, we can see that its solubility is 35.9 grams of salt divided by 100 grams of water. So if I took 100 grams of water, which remember the density of water is about 1 gram per milliliter. So if I have 100 grams of water, 100 milliliters of water, I should be able to dissolve 35.9 grams of water. Okay, but there's one more thing. Solubility is temperature and pressure dependent. So if you look at the top of this table, it says solubility in water at 20 degrees Celsius. So if I have 100 milliliters, 100 grams of water at 20 degrees Celsius, I can dissolve 35.9 grams of salt in it. If I were to increase the temperature of the water, let's say I increase it to, I don't know, 40 or 50, then hypothetically I should be able to dissolve more of the substance in there. The reason why is because as we heat the substance, the thermal expansion dictates that I'll have more space between the solvent particles. And if I have more space between the solvent particles, then more solute can dissolve as a result. And so what we see is for substances, as we heat the solvent, the solubility will decrease. As we cool the solvent, the solubility, I'm sorry, I might have said that wrong. As we heat the solvent, the solubility increases. As we cool the solvent, the solubility decreases. So in warmer solvents, I can fit more. In cooler solvents, I can fit less, because it's all about the spacing between the particles and how much can fit between those particles. So if I compare the solubility of salt, which is 35.9 grams per 100 grams of water, to that of another salt, baking soda, sodium bicarbonate, I can see that the solubility of baking soda is far less. It's 9.6 grams per 100 grams of water. Okay, so we could see that the solubility of the different substances will vary. For washing soda, which is like what might go in your dishwasher, or sodium carbonate used for a lot of different applications. 21.4 grams per 100 grams of water. Lye, which is drain cleaner, 109. That's a very large solubility comparatively to the other ones in this table. And sugar. If you go down to sugar, sucrose. Sugar is interesting. You could fit almost, you can fit double the weight of sugar in water. So what I mean by that is if you have 100 grams of water, you could fit at least 200 grams of sugar in that water before it starts to not dissolve. Okay, and so that's kind of fabulous, and that's actually how we make syrups. That's why syrups are so viscous. Is because the reasons why syrups are so viscous and thick is because we have so much solute and so little solvent present, and that it's kind of on its way to becoming more of a solid and less like a liquid. Kind of interesting. So you can see that the solubility of sugar is very large compared to other substances. If we get down to gases, the gases have very low solubilities, and this should make sense because solids, when they dissolve, they'd want to stay in solution because they're solids. They're typically denser than the liquid, and so they're not going to really go anywhere. Gases, however, since gases have such a small density, they have a tendency to escape the solution. Okay, they don't really want to stay in solution. They don't want to stay stuck between all those solvent particles. They want to spread out. They have lots of kinetic energy, and so since they want to spread out, if they find themselves at the surface of all of that solvent, at the surface of that solution, they're going to simply escape. Okay, and so when the ability for these gas molecules or gas particles to move around very quickly in a solution makes it so that it's very difficult to get them to stay in solution. So therefore, their solubilities are very low. However, they do have some solubility nevertheless. We can see hydrogen has 0.00017 grams per 100 grams of water. Oxygen has 0.005 grams per 100 grams of water. And carbon dioxide, comparatively to hydrogen and oxygen, has actually a very large solubility of 0.16 grams of carbon dioxide per 100 grams of water. Okay, you might say, oh, well, 0.16 grams of carbon dioxide per 100 grams of water, that's not that much. But if you think about it, remember, carbon dioxide is a gas. And so a lot of the carbon dioxide is not going to have a ton of weight because by virtue of it having a very low density and it being a gas. And so that's precisely why we use it in our sodas, right? So if I want to make a soda water, what do? Well, I take water and I can either bubble carbon dioxide through it and some of it will dissolve, or I could take water, have carbon dioxide and pressurize it and get it into that solution, and that carbon dioxide will stay to some extent. And so, but like I already mentioned, gases don't really want to stay in solution, okay? And this is why, for example, think about when you buy a bottle of soda, or like let's imagine a 2 liter of soda, right? So how does the company get all that carbon dioxide in there? First, they take the bottle, they add their drink, and then they pressurize it with carbon dioxide, and then they quickly seal it. So it traps all of that carbon dioxide in at a high pressure, and so therefore they could ship it wherever they want, and all of that carbon dioxide will stay in solution. But the carbon dioxide doesn't want to stay in solution, so the instant you open that bottle or can of soda, it's going to go tsh. It goes tsh because it's releasing pressure, first of all, and right after it releases pressure, what happens? All these bubbles start coming to the top. We have this initial fizz that develops, and that's because the carbon dioxide doesn't want to stay in solution. The pressure was already holding it in solution. It was holding it in place. But you relieve the pressure, so now all of the carbon dioxide wants to come out of solution. Okay? How do I get even more of the carbon dioxide out of solution? How do I free it up? Well, I give it the opportunity to arrive at the surface and leave. So if I were to take a soda and shake it, what happens? It explodes because all of the carbon dioxide is suddenly rushing out of solution. And so if I were to take a thing of soda and shake it, I would get all the carbon dioxide out of it, and it would be flat. It wouldn't have any fizz to it because I've removed all of the gas. Okay? And I don't know if you've ever realized it or not, but that's why we call it carbonation, is because we're using carbon dioxide. If we were using a different gas like oxygen, we'd call it oxygenation or hydrogenation for hydrogen gas. Okay? So it's called carbonation because of its carbon dioxide gas. So here's a graph of different substances. You can see if you look at the red line, we have potassium nitrate, and this is a graph of solubility versus temperature. So this shows the effects of how the solubility will change as we change the temperature. And so at very low temperatures, the solubility will be low, and at very high temperatures, the solubility will be very high. And that we already went over that, so it's based on the spacing between the particles. When the solvent is warmer, there's more space between the particles because the solvent is expanded, and so therefore more can dissolve. If it's colder, there's less space, and there's going to be less going to be dissolved. However, different substances are more susceptible to changes in their solubility based on temperature. Okay, for example, potassium nitrate, it's a little under 20 grams per 100 grams of water at 0 degrees Celsius. Okay, so it has a solubility of roughly 18-ish for its solubility at 0 degrees Celsius. But if you were to change the temperature to, let's say, 50 degrees Celsius, then it's going to be it's going to increase its solubility to almost 80. And if you increase the temperature to 90, then it's going to be roughly 200. And so the solubility increases drastically with an increase in temperature for potassium nitrate. And then if you look at this graph, we have lines for sodium chlorate, potassium bromide, and so we see the solubility varies based on the temperature. Some substances, the solubility does not change that much with temperature. For example, sodium chloride, table salt. The solubility of table salt at 0 degrees Celsius is just under 40. And if you go from 0 to 90 degrees Celsius, the solubility is, again, right around 40. So we don't see much fluctuation in the solubility for some substances, but we see for other substances, there's a lot of fluctuation. Okay? And so when you are trying to increase the solubility of salt using the temperature difference, that's not going to be very beneficial for you for sodium chloride. And so these are all dealing with saturated solutions. Okay, a saturated solution is a solution that has as much solute in it as possible. Okay, you can think of it like a sponge. If I have a sponge, a dry old sponge, I can pour some water on it, and the sponge is going to soak up that water. I can keep on adding more and more water to that sponge, and it will absorb it. It will get to a point, though, where it can no longer absorb any more water. At that point, we say it is saturated. So a saturated solution, on the other hand, is one that doesn't have any more space for solute. Okay, so if I take a beaker of water and I put a spoonful of sugar, it'll dissolve. Put another spoonful of sugar, it'll dissolve. Keep on adding sugar over and over and over until it doesn't dissolve and it starts to settle on the bottom. At that point, I have a saturated solution. Okay, so a saturated solution is one that does not have any space between the particles. It does not have any more room between the particles for more solute. Whereas an unsaturated solution is a solution that has more space and we can dissolve more solute. So if I were to take the water and I put a spoonful of sugar and I stirred it and let it dissolve, okay, well, my solution is unsaturated because I can still dissolve a lot more in there. Okay, so saturated, I've dissolved as much as I can. Unsaturated, I still have a lot more room between the particles for more solute to dissolve. There is a third type of solution that is called a supersaturated solution. Supersaturated solutions are solutions that have kind of been forced to hold more solute than they typically would. Okay, I'm going to say that again. It's a solution that has been forced to hold more solute, so dissolve more stuff than it would typically take. Okay, well, how does that happen? What we could do, so remember that the solubility is variable based on temperature. Okay, so let's say I take my water and I add 2 scoops of a substance and it dissolves. I take a 3rd scoop and it dissolves. Take a 4th scoop, some of it dissolves, but a little bit sits on the bottom. I've reached the saturation point of that solution. What I could do is take that solution, let's say it's at 20 degrees Celsius, and let me heat it up to 40 degrees Celsius. Okay, I heat it up to 40 degrees Celsius. The stuff that didn't dissolve, that was settled on the bottom, has now dissolved because now there's more space for it. And I take a couple more spoonfuls and I dissolve that at the higher temperature. It'll take 2, 3, 4, maybe 5 more spoonfuls of my substance. So I'm adding to the warmer beaker or the warmer solution, okay, until it starts to settle on the bottom. And I've saturated the solution at a higher temperature. A saturated solution at 20 degrees Celsius might take 3 or 4 spoonfuls, but a saturated solution at 40 degrees Celsius might take 8 or 9 spoonfuls. I can dissolve a lot more at the higher temperature. So here's what I do to get a supersaturated solution. I dissolve more at the higher temperature, and then I slowly and carefully lower the temperature back down. When I do that, most substances, most solutions will crystallize. The excess solid that doesn't fit in the solution at the lower temperature will start to form solid material. The particles get squeezed together and they start colliding, and when they collide, they start to stick and crystallize and form these crystal structures. However, some solutions will not do that. They'll allow the solute to stay in solution until there's some type of disturbance that will allow them to rapidly crystallize. And so a supersaturated solution is one that has more solute than a saturated solution at the same temperature. And it's created by dissolving that extra stuff at a higher temperature and then slowly lowering the temperature back down. At that point, it can be very rapidly crystallized. I'm going to show you a video of a solution that would do this. It's called sodium acetate. Let me pull it up on YouTube real quick. Let's see. So we have a supersaturated solution, and you can see it's everything is dissolved. I don't see anything sitting on the bottom. So what they did is they heated this up, they dissolved as much as they could, and then they lowered it down in temperature. And so now what they're going to do is they're going to introduce a small crystal of the sodium acetate, and that small crystal will cause a disturbance, and it will cause a chain reaction of crystallization. And so that one little piece of the crystal, all those solute particles that are dissolved that encounter that crystal and they bump into it, they'll just stick to it. And then more will stick to it and more will stick to it, and this crystal will start to develop and grow outward. Okay, so let's watch this happen. So they're taking the crystal, they're adding it in, they're going to keep it on a little stick. You see the crystal expand outward. It's not creating light. It is, however, an exothermic process, and it does create heat. So that is a supersaturated solution. And so a seed crystal of sodium acetate is added to a supersaturated solution. The excess solute immediately forms a solid. The solid continues to form until the solution is saturated. And so all the extra will come out and crystallize. And so, like I said, when some solutions form, it's going to be endothermic. When some solutions form, it's going to be exothermic. So it depends on the substance that you're dealing with as to whether it's going to be endothermic or exothermic when the solution forms. And it's going to have to do with the bonding of the substance. And so that one, the solution was already formed and it was crystallizing, and so that ended up being an exothermic process as we go from being in solution to being a solid. We already talked about this a little bit, but we could also alter the solubility of a substance using pressure. And so if I were to have a pressure over a solution, that makes it so that particles don't want to come out of solution because there's no room for them above the solution either. Because remember, if you have pressurized gas, you have a lot of extra gas particles, right? And so if you have all those extra gas particles, there's not as much room for these gas particles to come out of solution and be up there with the other ones because there's so many already. And so if you pressurize the solution, what you can do is you can force these gas particles to stay in solution a lot easier, okay? And then so that's what's happening with the soda here. We pressurize the bottle, and that makes the gas, the dissolved carbon dioxide, stay in solution. As soon as we open it, we depressurize it, the gas escapes, and now it's a lot more likely that gas particles are going to come out of solution and into the air. So if you're trying to have something stay fizzy or carbonated for a longer period of time, you want to keep it closed, and additionally, you want to keep it cool, because by keeping it cool, you're making it so those particles aren't moving as quickly, and if the particles aren't moving as quickly, they're not going to be able to escape as easily, okay? So you can think of it like, so when solutions are warmer, all the particles are moving a lot more quickly. There's a lot more energy, so a lot more kinetic energy associated with that. And so if there's a lot more kinetic energy, these gas particles are going to come to the surface more often and escape as a gas, okay? But if you cool it down, the particles are moving a lot more slowly, and the likelihood of them coming to the surface is decreased. Therefore, it will stay carbonated for a longer period of time. So if you're trying to keep something carbonated for a longer period of time, you want to make it sure it's cool, and you also want to make sure that it's sealed. And that's it for this section. So we now kind of have a little bit of background with concentrations and describing them. We know what solubility is. We're familiar with saturated solutions, unsaturated solutions, and supersaturated solutions. And then we know how pressure and temperature can affect the solubility of gases. And so I hope that was helpful for you.